Section 9.4 is areas and lengths in polar coordinates, or the areas and lengths of polar curves. Um, it's essentially two formulas, but being able to apply them is going to be very important. And we have to remember that I put a lot of emphasis in 9.3's videos or the polar coordinate videos on how these curves are formed when we travel in the positive direction along their domains and understanding what part of the curve we're at. So that's going to go a long way in setting up the integrals and using the area formula that we have below. So to begin, we have the area enclosed by the polar curve r equals f of theta, for theta taking on values between a and b or alpha and beta. Typically it's alpha and beta. In this case, this should be an alpha and that should be a beta to be more accurate, is given by the formula a equals integral from alpha to beta 1/2 r squared d theta. Since r is f of theta, we could always swap out r to be f of theta quantity squared in this integral formula, and that might be a little bit clearer on what we need to do. But to get an idea of where this formula comes from, let's consider it in this fashion. 1/2 r squared d theta. D theta is some small angular wedge. It's just a little infinitesimally sized angle, just like dx used to be a infinitesimal width on the x-axis. Now, so it's an angle in some sense, and if we were thinking about a circular sector, like we have highlighted right here, this a sub I, this little sub area in our region from alpha to beta in terms of angles for our given curve r equals f of theta. But if we treated this as a circular sector, which it's not exactly, but it can be approximated by one. And as we shrink d theta to be smaller and smaller, or if we treat d theta as it's understood to be infinitesimally small, then this is an exact approximation for this integral. But anyway, d theta is an angle. R squared is the distance from here to here. So it's the radius of this circular sector. So 1/2 r squared d theta, or 1/2 r squared theta, recall is the area for a circular sector with angle theta and radius r. Only thing that's changed now is this is d theta, and we're thinking of it as this infinitesimally small approximating circular sector. Now that's where the integral formula comes from, right? Then of course we would do so for infinitely many of these circular sectors in here, and we would add them all up with the summation, take the limit as n goes to infinity for the number of circular sectors that we're doing, and that's when delta theta becomes d theta exactly, and we have this integral formula right here. So that's a really brief sketch of where the formula comes from and a little bit of why it might make sense as we're using it. So let's jump into finding the area enclosed by certain regions of certain curves. They ask us to sketch the curve and find the area of the region enclosed by this curve for theta between 0 and pi over 6. The curve is r equals cosine theta. Now, r equals cosine theta, that's a circle with radius 1. It's tangent to the pole, and it has a circle of diameter 1. Right? So as we've drawn it here, unfortunately, it's quite small. R equals cosine theta is just this circle right here. Like I said, it's tangent to the pole. It has a diameter of 1. They've asked us to find the area contained in this region from the angle 0 to the angle pi over 6. And that's really essentially what is sort of marked off in red here in this little range right here. So if we imagine these curves as you know, the way these curves will enclose a region would be to start at whatever the beginning angle is and stop at the ending angle. And whatever is swept out by this curve, in other words, the blue line right here, or the blue arc of the circle, then that would be the region that we're actually looking for. It's bounded by alpha on the left, or the lower portion. It's bounded by beta in the upper portion of that sector, and it's bounded on the outside by the curve itself, which is just that circle of radius 1. So this is one of the easiest ones to set up. They give us the endpoints from 0 to pi/6. So that's how we set up our limits of integration. The formula says it's 1/2 r squared d theta. Well, r is cosine theta, so that'll be cosine squared theta for r squared d theta, and we've already factored the 1/2 to the front of the integral. So this thing is a pretty straightforward integral to handle. The antiderivative of cosine squared theta is the following: 1/2 theta plus 1/4 sine 2 theta. And then we've got to evaluate this from 0 to pi/6. And I really left those details up to the reader to determine. There's not much work to do there other than to evaluate the definite integral, or to evaluate this function at those endpoints. We've already found the antiderivative. But remember from chapter 6, or our techniques of integration, that this is the antiderivative for that integrand. So not much to setting that one up. It's really nice when they happen to give us the limits, or the angle values here, so we have the limits of integration. It's more of a question of when curves intersect, and we'll get to one of those momentarily. But before we get too carried away with area, let's have a look at arc length. Arc length for polar coordinates or polar curves. The formula looks somewhat similar. The common theme for an arc length formula is that there's a square root inside the integral, which will complicate our problems in many cases. Note that anything that you're expected to find exactly, there's probably going to be a trick to, or some kind of algebraic or trigonometric trick. You just have to find it or be aware of those sorts of things. Now, r is f of theta. Theta is ranging from a to b, or alpha to beta, however we might want to write that. And we set up our integral as follows. R is the function f of theta. Dr d theta is f prime of theta. That's the derivative of the function of theta with respect to theta. We square r, we square the derivative, and of course we integrate everything with respect to theta. Now, the book has a nice sketch of this formula and a motivation for where it comes from and why it makes sense. It's not necessary that we have a very sharp grasp of that, but some awareness of that might help us remember this formula and understand exactly what we're doing. But apart from that, these will look very similar to other arc length formulas. So find the exact length of the polar curve. R equals 5 theta, for theta taking on values between 0 and 2 pi. So again, everything is sort of spoon-fed here. We've got angles from 0 to 2 pi. R is 5 to the theta. That is an exponential function, 5 to the power of theta squared. So that's r squared there. Dr d theta, what's the derivative of r prime? Or sorry, what's the derivative of r? What is r prime? If r is equal to 5 theta. Well, one way to get there, if we forgot how to do that, this is a nice review from Calc 1. Take the natural log of both sides of this equation. What happens? We have natural log of r equals natural log of 5 to the theta, and the exponent rule for natural log says we can bring down theta as a multiple of natural log of 5. So bringing down the exponent from the argument of the log. It's the power rule or power law for logs. Take the derivative with respect to theta of both sides. That's going to be done implicitly over here because r is implicitly a function of theta. So we have 1 over r for the outer derivative. Then the chain rule, the derivative of r with respect to theta, we'll just call it r prime or dr d theta, whichever you prefer to write here. On the right-hand side, take the derivative with respect to theta of this, and we just have natural log of 5 times 1. And that's this right here. Solve for r prime. R prime is equal to r times natural log of 5. Well, r is 5 to the theta, so we can come out of this completely and write it in terms of theta. R prime is 5 to the theta natural log of 5. No, that's the long way to get there. Note that we could have just gone to the calculus book or looked it up online. What is the derivative of an exponential function? A to the x or a to the theta, where a is some positive real number. But if you forgot how this comes about, how you find this, then that's a nice little sketch from Calc 1 to have a reminder for. So we've got all the pieces. This is r prime. Let's take r prime, plug it in here, and square it. So we have 5 to the theta, natural log of 5, squared. We've already taken care of this exponential situation. 5 to the theta to the second power is 5 to the 2 theta. And down here we'll have, again, 5 to the 2 theta, multiplying those two powers, and then squaring natural log of 5 leaves us this term right here. So 5 to the 2 theta factors away from both of these terms. This is looking pretty good. We have 5 to the 2 theta, and then times, this is just a constant, so we don't really care what it is. It's just times a constant, I guess, all underneath the radical. And 5 to the 2 theta, let's take this slowly, is 5 to the theta squared. So we can factor that apart. What's really happened here, we don't see, because this is kind of a fast step, is that the integrand has been written as 5 to the 2 theta square root of that times the square root of, well, all the stuff that's in the parentheses. Okay, we can split radicals over products, and we did. We split it over this product right here to have the first radical and then the second. Well, 5 to the 2 theta square root of that is just 5 to the theta, so that's this component right here. Okay, this is just a constant like I noted before, so we'll move it out in front of the integral altogether. Square root or not, complication or not, it's kind of a mess, but it's just a constant with respect to theta. It sits out front, and we don't really have to think about it much more. Now, let's see, we have the integral from 0 to 2 pi of 5 to the theta. Well, what's the antiderivative of 5 to the theta? Very similar to how this thing came about. We could ask what the antiderivative of this would be. And, well, I'll tell the reader right now that it's just 5 to the theta over natural log of 5. And then I'd say that you could check that. If this is our antiderivative, then what's its derivative? Well, when you take this thing's derivative, the numerator is going to be 5 to the theta times natural log of 5, and these two things are going to cancel. So we'll just have 5 to the theta. So this, in fact, is the antiderivative of this function. I'm sorry, of this function. So we've got it. And natural log of 5, let's not panic. Remember, that's just a constant as well. So this thing, we can factor it out also. And we've got one big constant out front here with our given constant, and then this new natural log of 5 underneath it. And then we go 5 to the 2 pi minus 5 to the 0, and that's just 1. 5 to the 2 pi minus 1. And this gives us our exact answer right here. It's a bit of a mess, but it is in fact exact. One thing I want students to be careful of, don't simplify this radical. Square root of 1 plus natural log of 5 squared is not 1 plus the natural log of 5. Remember that. We cannot split the radical over a sum. So there it is. There might be one small question about finding this antiderivative. If there is, I suggest going back to whatever chapter covers logarithmic derivatives or exponential derivatives from the Calculus 1 sections and getting a little refresher on where that comes from. It should be done in a similar method to this. It could also be argued through this work to more or less deduce that it must be something of this form. But anyway, that's for your own review. One more thing I want to look at before closing this first video of the area and lengths and polar coordinates set is finding the intersection points of polar curves. This is going to come up quite a bit because we're going to be asked in problems to find the area contained by the region, contained within both curves, within two curves. Possibly we'll be given two polar curves and asked to find the region enclosed by those curves. So in order to do that, we'll need to know where these curves intersect each other. So in this case, this is just that form of a problem right there. Find the point or points of intersection of the curves R1 is 1 minus cosine theta, R2 is 1 plus sine theta. So just like you would for Cartesian functions or equations, set the two dependent variables equal to each other. R1 equals R2, just like Y1 used to equal Y2. Then this function is equal to this function. And now we just have to get to work solving for each. Subtract 1 from both sides. And now we have negative cosine theta equals positive sine theta. Divide by cosine theta on both sides. That's the equation we ended up with after subtracting 1. Now we're dividing by cosine theta on both sides. We have a negative 1 on the left. and we have tangent theta on the right. Sine theta over cosine theta is that. So tangent theta equals -1. That's 3 pi over 4. Technically, it should, if we use the arc tangent, we should have written -pi over 4 and then plus k pi. But and then these are integer multiples of pi. In other words, any positive, or sorry, any whole number, positive or negative, where k is any number in the integers. Okay, k is any element of the set of all integers, positive or negative whole numbers. So if we subtract pi from this, we'll end up with -pi over 4, and we'll have exactly the point that maybe we would have started with, but nonetheless, this characterizes them all. Now, we're not so much worried about this general characterization of these as much as we're concerned about which of these angles we're going to need to pick from the list. Because depending on what region we're talking about that's enclosed by this or asked about otherwise, we're going to have to find different angles where these curves might intersect. So having the most general form like this is useful, but you won't need to use all those angles when you set up your integrals in the future. So in the next video, we will talk about finding the area within certain curves, parts of certain curves, and we'll talk about finding the area enclosed by two different curves, and they're going to intersect each other, and we'll definitely have to use this tool.